Good.
So we are very happy to have Volker Schomerus from DESY. He will tell us about perturbative string duals.
Okay, yeah, it's a great pleasure to be here and today to do this online. Very difficult for me to travel right now for private reasons. So I'm happy at least that this online version is possible, although of course I would have very much preferred to visit the group in Chicago. Now I'll be talking about a that I wrote with Yasuaki Hikida back in December. Should say that after that I had to finish two big bootstrappy papers, so I haven't really thought too much about it. And I'm also very grateful about the opportunity today to kind of talk about it again, and especially in front of such an expert audience that I'm looking forward to discussing with you. Now, I'll start this talk is mostly, and of course I encourage you to ask questions. The more questions I get during the talk, the more I feel that there's an audience. The main subject of the talk is a formula that I want to show you. But of course, in order not to just talk about one formula, I will try to embed this in a little bit of a story. The way I started, it might be a tiny bit too general for this audience, but then we can get through this quickly. So let me give a little bit of the context how I got interested. In fact, more than 10 years into this, but of course, most of the time unsuccessfully. So you all know, of course, that more or less exactly to the day 50 years ago, Hooft wrote his famous paper on the planar diagram theory for strong interactions, in which he pointed out that if you take large N gauge theory computations, where you have these double line propagators and vertices, 3-point and 4-point vertices if you want, and then build diagrams, you can actually organize these diagrams according to a kind of a string loop expansion. So there is a way to associate a genus of a surface to these diagrams using this formula where you take 2 plus number of propagators minus number of loops minus number of vertices, and that gives you a genus. And then the gauge theory computation, which depends on the coupling constant lambda of the gauge theory and on n and the number of Kellers, will have some kind of expansion of this form that very much resembles the form in which we would write string theory calculations, the string loop expansion. Now, of course, again, this is, of course, extremely well known to you. So then, of course, yeah, this by itself, of course, is not necessarily useful until you have a prescription how to compute these functions that appear in the string loop expansion down here, these functions of the genus that depend on the coupling. And of course, again, as you all know very well, this was what was achieved more or less 25 years ago, that Maldacena gave a prescription for how to compute these quantities, at least for a restricted set of gauge theories, by suggesting that they can be computed through strings propagating on ADS backgrounds in one-dimensional higher. And in this context, of course, the coupling of the gauge theory was related to the natural scale, or no, sorry, not to the scale, to the parameter of the string compactification, namely the radius of the compactification measured in string length, by this formula, which meant, of course, or means, of course, that these calculations, I mean, the string theory, of course, is very easy to calculate when the curvature radius is small. Then you can do supergravity computations, and that probes sort of the large lambda, the large coupling region. Of course, again, that's all very well known. And of course, the advantage of this is that you get easy access, in fact, to gauge theory quantities at infinite coupling. The disadvantage, obviously, is that it makes the derivation very complicated, because somehow this duality, this Hooft-like relation between string and gauge theory, is intertwined with a strong weak coupling duality. And again, of course, that's all very well known. So the next step is that, of course, one should observe that, of course, this prescription that Maldacena gave for computing these quantities fg of lambda is not necessarily unique. There could be other descriptions which might be good in other regions of parameter space. And we know all this very well, of course, in the context of Falabi-Yau compactifications, where we have just a setup where we could have like dual kind of Landau-Ginzburg phase or Landau-Ginzburg description or Gepner model prescription, which is a fine description for the string theory. And it becomes sort of easy to use at a very different point in the parameter space, in this case, the parameter space lambda. So the conclusion is that there could very well be, of course, non-geometric worldsheet theories that allow for perturbative computation, in particular around the point lambda equals 0. And if such a prescription existed, of course, that would be fantastic, because one would really hope that one could derive these things by just rewriting. This is the process that I call engineering. So you would take your gauge theory, and just rewrite the gauge theory perturbation expansion in terms of a string theory, and thereby engineer a string background. The disadvantage could be at first that, of course, it doesn't give you direct access to lambda to infinity strongly coupled gauge theory, which is a feature of holography that we're very used to. On the other hand, I would want to argue that in some sense, this is not such a serious drawback, because like one way I would want to argue is that when we look at n equal 4 super Young-Mills, I mean, the main thing is really that we are able to rewrite gauge theory as a one-dimensional quantum system. And in that case, of course, an integrable one-dimensional quantum system. And then all the power of this one-dimensional quantum system can be used to do calculations. And the prototypical example of this is this famous Beiser-Isen-Staudacher equation, which is a very simple equation. You don't need to know anything about ADS to write it down, not even about gauge theory. And it produces beautifully for you like an exact result for the Casper anomalous dimension. That means sort of the exact blue and red trajectory in n equals 4 super Young-Mills, planar n equals 4 super Young-Mills, and that means also the leading logarithmic approximation to even QCD. So I want to argue, so this is what I call perturbative holography, or not only, so perturbative holography is a holography that where you have a non-geometric worldsheet description that works best around lambda equals 0, and engineering such a thing is really kind of just rewriting the gauge theory expansion in terms of string theory expansion. Now, the question is, can one find examples? And to be honest, yeah, I tried. I alluded to the fact that I started this long time ago, about 10, 12 years ago. I tried with n equals 4 super Young-Mills, and I failed. For 10 years, I didn't even want to think about it, because we had actually written 2 drafts already of the paper, but somehow it didn't feel fully convincing at the time. And then in 2021, of course, after all this beautiful development in low-dimensional holography in particular, Eberhard issued a paper in 21 on a perturbative CFT dual of ADS3 with pure NS flux. And that was the moment when I felt like maybe to go back to this problem and try, at least in this now very well controlled context, to do this kind of engineering that I've tried to sketch, namely to take really the perturbative expansion of some gauge theory. In this case, of course, it's a 2-dimensional CFT, and to try to rewrite it in terms of a string theory. So that brings me sort of to the main result that I'm going to present today, and then the outline. So maybe, is there any questions on motivation so far? Or comments? Okay, it probably was too general for you. So the theories I'm going to study, as I said already, is not n equals 4 super Young-Mills, but it's a 2-dimensional family of 2-dimensional CFTs. And I will describe them in more detail in a moment, but I think most of you probably are quite familiar with these things. So it's a symmetric product orbifold in the first place that corresponds sort of to the free gauge theory. So you take some theory X and then tensor it with what's called linear dilaton. Again, we'll get to that in a moment. Linear dilaton with a particular background charge, which is parameterized by a parameter B. And then you take n copies of that, and you divide by the group action of the permutation group. That's the symmetric product orbifold. That's a particular CFT. And then you actually turn on some kind of interaction that I will also describe. That's here denoted by lambda, and that's the analog of the Young-Mills coupling to a certain extent that I'll describe better. And so I will take this theory, and then I will do exactly what I said. I will take correlation function in this theory, and I will rewrite them in terms of a string theory. So that means an exact bosonic string theory, C equal 26 theory with interaction. And I will do this in a way that it's guaranteed to reproduce order by order in the coupling and order by order in 1 over n, the correlation functions of the CFT. So I want to stress this very much. I mean, this is the proof here, of course, is not by computing quantities here, and then comparing them. Of course, there's has been a lot of work on that, and in this direction, including by many people here in the audience. But I will actually do this relation without computing a single correlation function, okay? And of course, in the light of what I said before, in terms of engineering, that's of course an important process, because even if I'm not able to solve my CFT or my gauge theory initially, I could, if I was able to rewrite it as a string theory and then could use the power of one-dimensional physics in order to do computations, I could actually learn something about the gauge theory that I wouldn't know otherwise. So that's why it's so important. That's why I stress in the context that I described that this relation that I will explain is actually established without computing a single correlation function. It's just a step-by-step equalities that I go through, and that will bring us to the string theory. So that brings me to the outline for this talk. In the next first section, I will actually describe the CFTs, these symmetric product orbifolds, and their perturbation. So that explains this side of the correspondence. Then in the second part, I'll prove an exact formula for a correlation function that's an auxiliary result in some sense. And then in some sense, this is sort of the main new result of our work. And then I will reinterpret that, or interpret that in the process of, in this context of engineering a dual string theory. And here, of course, in the last part, I will make heavy use of what has been understood in other work on the subject of these low-dimensional ADS CFT correspondence. Okay, that's the plan. Any questions? Okay, that's not the case. I don't know, maybe everybody here is an expert on symmetric product orbifolds. If that's the case, then somebody should at least raise a hand, and I could go faster now. Otherwise, I would kind of slow down a little bit at this point.
I don't think you should assume everybody in the audience is as familiar as.
Okay. Good. So I will talk about a little bit about the CFT in this case, and I will try to highlight the similarities with gauge theory, as you know, at large in gauge theory. So symmetric product orbifolds, again, you start with some kind of parent theory. I will discuss that in a moment. Now I call that for now just M. And then, as I just described before, you take n copies of this theory and you divide by the action of the permutation group. That's an orbifold theory. And in this theory, you have, as in any orbifold theory, orbifold CFT in 2D, you have twist fields. And these twist fields, of course, are labeled by conjugacy class of the orbifold group. That is, sorry, conjugacy class in the orbifold group. Yeah, these are labeled, of course, by permutations. For us, of particular importance will be the permutation of the twist operators associated with single cycle permutations of some length W. Single cycle, of course, you just have to give the length of the cycle. So that's just an integer. So, of course, a cycle of length 1 is trivial, but cycle of length 2 is just a permutation of 2 neighboring objects, and so on and so forth. So these, in fact, will play the same role as single trace operators in large gauge theory. That's why the single cycle permutation is sort of the single trace. Now, these operators these are fields in the CFT that have conformal weights, which are given by this formula, just determined by the central charge of the parent theory and the length of the cyclic permutation W. And I will now develop. So the operators, we will have a graphical. So I'm now reviewing work of Pachmann, Rastelli, Razamat that was essentially whose intention it was to kind of stress very much the relation or the similarities of this theories with perturbative gauge theory. And so the operators, the single cycle permutation operators, I denote by these kind of circles with like two W lines emanating. And these W lines, they actually are a little different from gauge theory. So in usual gauge theory, of course, you have double lines. The lines are of the same type here. In fact, the propagators are also double lines, but they have two different types of lines, dashed lines and solid lines. And so similarly, these guys here, these operators have these double lines emerging. So there's always a alternating a solid line and a double and a dashed line. And then you can do more or less like in Hoof's description of gauge theory, or you do gauge theory calculations. You can write diagrams in this theory. And so you would take some operators, if you have a correlation function of some operators with certain cycle lengths. So here I give an example of 4 operators that have cycle length 2. So they have 4 of these propagators coming out of it. And then you do contractions in different ways. So now there are some rules that are different, a little bit different from the gauge theory rules, but that's not so important. So in this case, you have 2 types of loops, dashed loops and solid loops. The number of dashed loops and solid loops has to be the same, and there has to be some condition on the cyclic order of fields along all as you go along a dashed loop. So for instance, this dashed loop here, I guess it's hard to distinguish the dashed from the solid. But if you go along the dashed loop, you will pass through these operators in some order, 1, 2, 3, 4, 1, and there should be always the same, and the same also for the solid loop. So these are some kind of extra technical conditions for admissible Feynman diagrams that you're not used to from ordinary gauge theory, but they are very well understood and they follow directly from the prescription. So as in ordinary gauge theory, you can now organize these diagrams in the loop in this expansion of correlation functions of twist operators in this symmetric product orbifold in some kind of loop expansion. And so the way you compute the genus of your surface is basically you take the number of the sum over all the cycle lengths, then minus the number of operators and minus 2r, the number of loops basically that you have in this diagram, and you compute 2g. So this is very much like in Hoof's description. So this here is the number of propagators minus the number of vertices minus the number of loops. And that gives you the genus. And so the claim is that this organizes all this correlation function computation symmetric product orbifolds in a loop expansion, very reminiscent of ordinary gauge theory computation. Now, that's what I wanted to say about the similarity with gauge theory. Of course, for practical computations, there's another very, practical computations are always hard, but there's an important fact that these Feynman graphs that I just described with these rules that I just gave or sketched, they actually can be seen to correspond one-to-one with R-sheeted. So R is the number of solid loops or dashed loops in the diagram, R-sheeted ramified coverings of a sphere with ramification points of order WA. WA are the cycle lengths at certain points Z, that one can compute from the insertion points of the twist fields on sigma G. So again, that's something that you can look up in the paper of Razamat, Rastelli, and Pachmann. They describe this relation. It's not so difficult to understand. And of course, these ramified covering, you can then describe in terms of what's called the covering map. So that means that there's a map. I should maybe call it F of gamma, because I called gamma this Feynman diagram or these fat graphs that I described before, but I will identify, because as I said, it's a one-to-one correspondence. I will identify this covering map with the graph itself and use the same letter gamma for that. That's the map that comes from a genus G surface. Genus is computed by the formula I gave from the previous slide to the two-sphere with the following conditions, that near the ramification points, ZA gamma, it has an expansion which looks like as follows. So it gives the leading term is the XA, the insertion point of your field, twist field on the two-sphere, S2. And then for a while there's nothing until you hit this, come to this term with the power WA. So WA, non-trivial is at least 2, but could be higher. There's a cycle length again, and there you get this behavior with an undetermined coefficient at this point, A gamma. So these, it turns out that by this condition, this covering map is more or less, I mean, has no free parameters. It's computable. It's up to some discrete choices. And so you compute from the data that you give, you can compute both these coefficients as a function of the insertion points of the twist fields, as well as the position of the ramification point, ZA, on the Riemann surface sigma G. So this is computable data, okay? So you give yourself the data that is there in your initial CFT, the cycle length, or the length of these operators, the insertion points on the worldsheet of these operators, and then you can compute these data. This is computable, but it very easily gets very hard to compute, even for relatively small correlation functions. Now, if you are able to compute this, so maybe one more comment is that this covering map that you compute by this, I want to point out, automatically has to have poles, not just zeros, or kind of, it doesn't have zeros actually, but not just, so near these ramification points, of course, the derivative of gamma has zeros, right, of order W minus 1. So it's clear that by standard functional theory of complex functions, this derivative of gamma with respect to Z must also have poles. And in fact, this number R that we computed before, the number of solid or dashed loops, just gives the number of poles of these functions. And since the whole function was sort of computable from the data up to some discrete choices, also the positions of the poles, which I will denote by VI, they are computable from the data of the CFT quantity that I want to compute. And so if I was able to compute this covering map for a given fat graph gamma, then I could compute or relate the correlation function of these twist fields. So I guess this notation I'll explain a little bit more in the next slide. So these would be dressed twist fields, not just twist fields, but they're dressed by some extra contribution coming from the parent theory. You insert them at these points XA on the two-sphere, and you can, in principle, relate that then, or also in practice, relate that to a calculation of correlation functions in the parent theory, which is performed now on a genus G surface. And the fields in the parent theory are now associated and inserted at these points on the covering space that are computed sitting here. And there's a very complicated looking prefactor here that you have to compute given all the data. In particular, you have to compute that from the covering map, if you were able to compute the covering map. Okay, many people have worked on that. This is a standard technology for computational orbifolds, and in particular in this context, also has been a lot of research on the subject, including, of course, by people in this audience. All right, so that being said, now let's come to this. So these are the generalities on the symmetric product orbifold. And now let's describe the parent theory that we want to study. Our parent theory M is now given. That's what's the proposal of Gabadil and collaborators, in particular, the one that appeared in Eberhard's paper from 21 that I was referring to initially. So the parent theory that you take is you take some CFTX. It's your favorite CFTX. The only thing that you you have to have a central charge 26 minus 3k over k minus 2, where k is some number. So you pick this such a CFT, parameterize the central charge to k, and then you multiply that with a linear dilaton. So it's a free CFT with a background charge, free boson in 2D with a background charge. And the background charge you have to adapt to your choice of x. And so the rule is that for the background charge, you choose this q phi, which is b minus 1 over b, and b, I guess I had the relation before, 1 over b squared is k minus 2. Okay, so if you have k, fixed k here, then you can compute the b from there, and from there the background charge of the linear dilaton that you want to choose. And so this parent CFT has, of course, central charge, which is just the sum of these two contributions. And so if you plug that into this construction, take M, this product of these theories, then then you get this symmetric product orbifold that will be sort of our main player in the following. Now, in this theory, and now comes this notation that I wanted to explain. In this theory, of course, you have fields, fields which are associated. So you make a choice of a state or field in this CFTX. I call that psi, and then you can upgrade that to a field in your symmetric product orbifold, and that's notation here. So what it looks like is, so the W here denotes sort of the twist field. Maybe I should have written this out. I don't know, maybe I can do this now. The twist field, I try with my fingers. So what is V, W, alpha? You can see that, right?
Yes.
Yes.
Okay, good. So psi x bar. Sorry, that's just done with my fingers, and I would have to start my iPad to get some more professional looking formula. So what I mean is basically you take the twist field that I had before with index W, and now you act with it. So the fields in the parent theory are product fields of psi. And then in the linear dilaton, we take these exponential vertex operators to, I had written this here, to alpha phi. So these you take in the twisted sector. So you impose boundary condition at this thing, which enforce these fields to have periodicity when you go around this twist field W times. Okay, and so that's so I erased that because it does look so ugly, but I hope it. So these fields have a conformal weight, which is given by this formula that I have here. By this formula, that's again computed according to the standard rules of orbifold CFT. He has inserted that the central charge is 6K, so he has central charge over 24. That was the formula I had at the beginning, and then comes his contribution from the operator in the matter theory. So that's the field, and of course we denote them again by this familiar vertices or familiar operators that I had before. And now comes the next observation, and that's I think made by several people. But so that in particular you can now build in this theory one of these operators that is actually exactly marginalized, conformal dimension 1. And so the claim is that this is the field which takes sigma 2, the twist field of twist length 2, and then multiplies it with e to the phi over b. And if you plug this in, I don't do this exercise for you here, but you plug the data into this formula here with the background charge that I chose, and everything I think is on this slide, then you'll find indeed that this field has dimension left and right moving conformal dimension 1. And so the proposal is to use that as a vertex in that theory. And so the vertex, so this is length 2, so the vertex has is a 4th vertex in this theory. Now, so the proposal is that this gives an exact some kind of interaction in this symmetric product orbifold. And that's very similar, of course, to standard Liouville theory. It's kind of a dressed Liouville interaction where the Liouville interaction usually is exponential field in phi. Remember, dilaton is, of course, a free field theory. So now it gets interaction. It's just coupled to this twist field, or the twist field is addressed with this piece. So like in Liouville theory, this will define, when we add this interaction, this will define the interacting theory. Of course, in some sense, an interacting theory without a real parameter. Like in Liouville theory, you probably remember that the coupling in front of this term, the Liouville exponential, is not really a coupling, because you can just absorb the coupling into the redefinition of the zero mode of the phi field. But it's certainly an interaction. Liouville theory is a very non-trivial theory, in spite of the fact that lambda is not a tunable parameter. All right, so that defines the theory we're after. That's the initial part of the talk. And so now let's summarize part one of my talk by stating the task that I'm setting to accomplish. So we want to compute correlation functions of these fields, in the symmetric product orbifold for any set of cycle length W, any set of alpha parameters that refer to this Liouville or linear dilaton momentum, any set of psi's states in the matter in this X theory for any set of X's, and with this parameter lambda turned on. Lambda is, as you see, sort of the strength of this interaction. And so here that means the following. So if we relate that to just doing symmetric product orbifold, we just expand the interaction, and then we get a sum over, again, all gammas over all covering maps, if you want, or all branched covers gamma, then the sum over all S, all powers of the interaction, and here we get this correlation function that we now can evaluate in this free orbifold theory. And according to what I told you 2 slides ago, of course, we can compute that. I mean, we can go from this description, which is a description of a correlation functions on the 2-sphere, we can pass to a correlation function in the parent theory on the surface of genus G, and then that looks as such. So now the fields are all inserted at this the branching points of the branched cover, as I described before, and these guys here are, same with these. And there's this complicated prefactor that I alluded to before. And of course, this side now requires, in particular, this prefactor requires that you would compute the gamma, this branching function, in order to be able to compute all this. So the genus of the surface that appears here is, of course, computed by this formula that I had before. So you put in your W's, the cycle lengths that you have, the number of fields that you have, and the order S that appears here, and then you compute this 2G. So sorry, R is of course the number of poles of here, as I pointed out before, in derivative gamma, or 2 R's. Okay. So that sets our task, and I hope I explained that reasonably. Okay, so our task is to compute these quantities in the perturbed, interacting, Liouville-like interacting symmetric orbifold theory. I want to compute arbitrary endpoint correlation functions for arbitrary lambda and arbitrary n eventually, or perturbatively 1 over n. And that means I have to be able to compute this quantity, or relate that to. Okay, so that's should define the task. I hope you're with me. Any question?
Yeah, this is a piece of the theory, right? So the piece of the theory that's accessible to conformal perturbation theory.
Right, right.
I mean, if we're going to buy the analogy to, say, Liouville theory, then we know that there's much more to the theory consisting of correlation functions that don't satisfy various momentum conservation constraints.
Exactly.
Which, I mean, colloquially in Liouville theory, one calls them, you know, sort of bulk. What you're describing here is what are sometimes in Liouville theory called bulk amplitudes. And, and so they're sort of not sensitive to the structure of the Liouville wall.
Completely, I completely agree with you. In some sense, I mean, we know, of course, that that Liouville theory is much richer, and what this kind of perturbative computation compute is sort of residues of poles of the correlation functions, right? When the momentum conservation, the special momentum conservation that you were alluding to, is satisfied.
That's right.
It does compute some data of the true answer, but of course not the full thing. So this is sort of this Gulian-Li type treatment of Liouville theory, right?
That's right. So,
yes.
and I don't know if this is the appropriate place to address the question, but one thing that held us up when we were thinking about this somewhat earlier than Lorentz is whether you can really define the theory for k larger than 1.
Yes.
Because k equals 1 is the dividing line where the slope of the linear dilaton changes sign.
Right.
So the reason we restricted our considerations to k less than 1 is that was the regime in which this Liouville wall was shielding the strong coupling region. Whereas for k bigger than 1, the linear dilaton slope is in the opposite direction. So in some sense, in that regime, this Liouville-like wall is shielding the weak coupling region, and there's nothing shielding the strong coupling region. In some sense, you're trying to define some kind of perturbative S matrix with this formula for k bigger than 1, where the strings are sort of free in some sense in the strong coupling region, and then they're trying to bounce off this Liouville wall. And so it's not clear that there is a sensible perturbative approximation. So do you see a distinction in your formulas between k bigger than 1 and k less than 1 in terms of their properties?
Yeah. So maybe okay, since you said it's so maybe we can come back to the question a little later towards the end.
Happy to.
But I agree with what you say. I think to some extent, of course, I think part of the answer we will get to a little bit later.
Okay.
If that's okay with you.
Sure.
But yeah, it's certainly totally right. I mean, so there is this issue, of course, if this theory, like a Liouville theory, of course, initially when people did the calculation, I mean, the question, was what this theory really is like. You can do this perturbative calculation again, computing certain data of a theory of which you don't know initially whether it even exists or not. I mean, the dot solution, of course, was found much later. So here we are in a kind of similar status. So now I come to the second part, unless there are other questions. I would come to the second part. And the second part, as I said before, somehow would be the sort of contains a technical formula that is sort of the main contribution, new contribution from our work in some sense. And so I will first describe a little bit of input, then I give you the result, and then I'll very briefly sketch how that's derived, and then we'll move on from that. So let me first talk about something. I'll call that SL2K Katsuaki-Kimoto theory. It's a free field theory that I'm describing, and I purposefully did not call it Versumino theory, although often it's not distinguished so clearly. But now I'm talking about a free field theory that has a content, a linear dilaton phi, which is not the same linear dilaton that we had before. It has a different central charge given just by B. Remember the one before had B minus 1 over B. And a beta gamma ghost system, which has central charge 2, with these choices of weights. And so the total central charge of this Katsuaki-Kimoto theory is given by 3k over k minus 2. Recall B minus 1 was k minus 2. Now, so this is a nice free field theory that you can have a lot of fun with. It actually has, I mean, that's why I call it SL2K. You can build from here an exact SL2 current algebra at level K. Formulas many of you probably know, and those who don't, doesn't matter so much. So this has a rich state space in some sense. What is very important to include here is sort of non-trivial vacuum of the beta gamma system, so-called spectrally float vacuum. And so normally, of course, the gamma on the ordinary vacuum of the beta gamma system, gamma being a field of dimension 0, would be constant. The beta would vanish, have a okay, the gamma would, if W was equal to 0, would just be 1. But in this twisted vacuum, in fact, gamma has a 0 of order W. And so that's a family of vacuums. So basically, you change just the quantization condition for your fields. You allow different modes. I mean, the annihilating modes of gamma, you shift. So, so the importance of this, okay. And then you can build vertex operators in this theory in the following. So you now so you have this. Okay, so you now take your CFTX. That's the same CFT that we had previously when we discussed the symmetric. I mean, the parent theory of the symmetric product Orbifold. And you take this SL2K Katsuaki-Moto model, which I just described, including these special sectors with these spectrally float fields, vacuum, spectrally float by W units of spectrally flow. And you build the following vertex operators from there. So you take a field of your theory X and multiply that with the field in your Katsuaki-Moto model. And the fields in your Katsuaki-Moto model, they look a little scary, but not so bad. So they have some kind of piece, which is sort of exponential in the phi field, so that carrying some kind of momentum J, subtracted off something depending on the W. Then you have here these vacuum of the beta gamma system, and then some powers of gamma in front of it. So these are vertex operators. And in order for these vertex operators now in this theory to be physical states, so they have dimension, conformal dimension left and right moving conformal dimension 1, you impose a physical state condition, and that's the physical state condition that allows you to compute. So given the conformal dimensions of psi, h and h bar, you can compute the indices m and m bar, that is the powers of these gammas here, using the physical state condition. Okay, and so then you get these operators in the theories. Again, it's a simple theory. It's a free Katsuaki-Moto theory multiplied with whatever x you have, and this is a theory which has by construction, in fact, central charge 26, because you probably, hopefully remember that my X theory had the central charge 26 minus 3k over k minus 2. So now if I add 3k over k minus 2, then I get a theory of central charge 26. It's free, okay, as free as X is. If X is interacting, of course, then it carries over, that interaction carries over. And it has this set of physical operators in the theory. Okay, so I think this is as much as you need to know about this theory. And so this is a CFT. And what I'm now going to show you is a formula that rewrites our correlation function in the symmetric product orbifold theory in terms of this CFT. So again, you remember from the last slide of the previous part 2, that our task was to compute this quantity. So this is for one particular choice of gamma. Sorry, the gamma is not in yet. So you want to compute this quantity here for given cycle lengths, alpha parameters, psi's, and then up to some order S. So these are the insertions of this interaction term that we talked about. And so, as I said, I will first give you the result, and then I'll explain a little bit how it's obtained. So you recall that I told you before that because it was a correlation function that we want to compute in a symmetric product orbifold theory, we can actually compute it in the parent theory instead and pass to the surface of genus G. And then the formula looks like this. Now we integrate here over over the insertion points y, of course, of these fields ya as before. And here we have all these fields inserted now at the branching points of your branch cover, which you have to compute, of course, in order to evaluate this formula, and it has this complicated prefactor. And so what we now did is we kind of used a machine that we had actually developed more than 10 years ago in a slightly different context. I'll talk about this in a little bit. We used the machine and transformed this formula into a new formula. And the new formula I'm going to show you, the new formula looks like this. So in this new formula, now everything, so this formula is a formula in this Katsuaki-Moto theory that we had before. So this formula is in the parent theory of the symmetric product orbifold. This one here is in the Katsuaki-Moto times X. And so so these fields phi here are in this Katsuaki-Moto theory. That's the ones that appeared on the previous slide. And so you see, of course, that there's fields associated to the branch points Z nu, so this is the same as Z nu gamma. So these are the fields associated with these. And they have, of course, a parameter, I mean, the spectral flow number W nu is related to the cycle length in the orbifold theory. Then we have operators like this, which are associated with the interaction in the symmetric product orbifold. And then you have a new set of operators here, which do not have no correspondence up here. And they are inserted in the poles of the covering map. So there were no operators here that sits, and I pointed out before that the covering map has to have poles because of functional analysis, but there were no operators. They are now, in this representation, we have operators sitting at the poles. So at every pole, there's an operator sitting. It has a spectral flow -1, and this is what it looks like. So that's a new set of operators. These are kind of more or less similar to those, except that somehow the J and the alpha, so the momentum in the Liouville direction, and here the momentum in the phi direction to J nu, they get these little shifts, but otherwise it's minor. But maybe most dramatically is that this complicated prefactor that appeared here times some factor that comes from the measure of the YAs, that actually can be written just as an integration over the insertion points of UA. So these are the branch covers, I mean the coordinates on the branch cover of the interaction terms in the symmetric product orbifold theory. And then when you do this, there's a trivial prefactor here, okay? So this is as we will see, this will be quite helpful for purposes in the next section. So that's the result, and in some sense, this formula is sort of the centerpiece of this presentation. I again want to stress that this is not there's no string theory on this formula. This is just a rewriting, yet another rewriting. I told you can think about symmetric product orbifold correlation functions in terms of these double line or fat graphs. You can think of it in terms of branch covers, and you can think of it in terms of correlation functions on in this Katsuaki-Moto theory times X. Okay, and
so the insertions, the S insertions where your cursor is, those are just the branch points of the branch cover.
These are branch points. So the Z's and the U's are branch points of the branch cover. The Z's are the branch points for the insertion points of the external operators. I mean, the ones that were there even in the unperturbed theory. And then the UAs here would be the branch points for these insertion points of the interaction.
Right. And so what's the last factor, the one that goes up to R?
So this is a new insertion. And
what
that's
do they represent physically?
Yeah, sorry, I'll show you a little bit where it comes from. But I mean, okay, this is sort of the I mean, that's the formula. The formula said if you want to reproduce this quantity here, this correlation function in the symmetric product orbifold theory or in the parent theory on the surface of genus G, you can do so in this Katsukimoto theory, but it comes at the price putting in these extra insertions at the poles. And so the advantage that you get rid of these prefactors.
So these poles are where the world sheet is doing what? Is it going off to infinity?
Yeah, yeah.
So this is like some long strings going off to infinity at the points R?
They are screening operators.
They are screening operators, yeah. But I mean, at this point,
okay.
I mean, they're not integrated, okay? So nothing here. So this is one thing that I wanted to point out. Nothing here, okay, except for this. These guys here, they are integrated because initially the interaction was integrated over, but otherwise nothing here is integrated. That's why it's not a string theory formula. It's just a conformal field theory formula, okay? So there's nothing integrated. These things are inserted at some particular points. Of course, if it was a string amplitude, we would expect to have integrations over the Z's and the V's. But it's not happening. It's not what we see here. Okay, so I'm actually not sure how I'm doing on time.
10 minutes.
10 minutes. Okay, so that's not much. So I wanted to show you a little bit. So as I said, this is a machine. I didn't tell you anything about the machine. We developed that a long, long time ago. I mean, 10 years ago, more than 10 years ago, actually 15 years ago, mostly to relate Wessel-Minowitten correlators to Liouville theory. And so somehow Wessel-Minowitten theory has a Katsukimoto representation in terms of beta gamma and the phi field. And we, by integrating out beta gamma, we could actually relate these things to Liouville theory at the expense of putting extra insertions into Liouville theory. It's there's a nice way of understanding that. And if I had time enough, I could explain some of the features that we see here from that. So we ran this machine in some sense here backwards. So we started with something that was like Liouville theory, and we tried to rewrite it in terms of a kind of a, if you want, more like Wessel-Minowitten or Katsukimoto type theory. So it's running the same machine sort of backwards. And it's not so difficult to understand some of the features, so that somehow there's central CFTs of different central charges that are compared, this extra insertion of extra operators and the shifts of operators. All these things can be understood quite easily. But I think I don't really have time to explain that. So if you want to get more details, I mean, okay, this is not a detailed slide, but it has at least some details. We can go back to that later. In any case, it's sort of it's a nice little piece of machinery. And this formula that I showed you here, and I'll show you on the summary slide for part 2, is an exact formula that you can prove rigorously. Okay, I didn't fully state it, but almost fully stated here, can prove rigorously in the way that I've described. So the result of this calculation discussion is that these correlation functions symmetric in the deformed symmetric product orbifold theory that we wanted to compute, which take this form, they can now be rewritten in this form, where you have for each operator in your symmetric product orbifold, you have a physical state, operator in this Katsukimoto times X theory. You have operators inserted where you had at the branch points for the insertion of the interaction that are integrated over, and you have an extra set of operators here with spectral flow -1 inserted at the poles of the covering. And so, as I stressed on the previous slide already, this is just a formula, yet another new formula for symmetric product orbifold. I mean, for these particular symmetric product orbifold correlation functions, that has some nice features. And probably the nicest one is that this factor, this theta, is gone here. But of course, the complication of evaluating this site is still the same. You have to kind of compute, if you're giving the data of the orbifold theory, you have to compute the insertion points. And of course, that means you have to compute the branch cover. So by itself, this formula is not that explicit, not more explicit than the original one, just simpler. Okay, so now that brings me to the last part, for which I have now about 5 minutes. Now we want to take this formula and put it into the context of the story that I tried to motivate at the beginning. So let me first phrase our statement on the next 2 slides, and then we'll see how much time I have to explain or give some supporting evidence. So our proposal, therefore, now was to say that, so we take this this theory here. I mean, so this is our proposal. I guess I'll relate it to the previous discussion in a moment. But so we take this theory, which is our Katsuaki-Moto free field theory, times X, actually. So the X CFT is sort of added here, whatever it looks like. So that I argued before is a theory which has a central charge C equal 26. So you can do nice string perturbation theory with it. And it has the current algebra symmetry, SU2K current algebra symmetry. And to this theory, we want to add 2 interaction terms. I call them phi minus and phi plus. So phi minus is constructed from a vertex operator with spectral flow number -1. It's given here. You can go back. So it's a particular operator that I described before. It's a satisfies physical state condition. It's this guy. And then a second one, which has a spectral flow +1, which we insert here. And I put here sort of a relative, so an overall constant I can always absorb. I put sort of a relative constant here in the second term. Now, I should say when we wrote the paper, we had not seen, we thought sort of this psi plus was entirely new. Later, we realized that Amit and Saki had worked in different contexts with similar set of screening charges. So they had already noticed that these particular operators, not just physical states, but they also preserve the current algebra symmetry. So when you add this interaction to your free theory, you're not destroying your current algebra symmetry. It remains intact. So these are screening charges in technical terms. And the phi minus here is actually a screening charge that is essentially a old-fashioned screening charge of the second kind, rewritten a little bit. So it goes back to the work of Beshatsky and Okuri, and also appeared recently in a related context in work of Andrea and Bob Knighton, just also before Christmas. The second screening charge here is somewhat unusual for, less common. It can actually be expressed entirely in terms of beta gamma system, and has a few features that maybe I have time in a moment to explain a little bit more. Now, naively, of course, the second screening charge that we insert looks like almost trivial in our context. Remember, it has winding spectral flow number +1, and so when you go our correspondence back, it maps to a symmetric orbifold operator with cycle length 1, and of course such things would be trivial. So it looks like it's almost a trivial insertion, but it's actually not quite trivial. And so now comes the proposal. So as common in this discussion, we now introduce these vertex operators. We deform them by a choice of x and x bar, which corresponds to the location of the orbifold theory on the 2-sphere. We inform these deformed operators. And as was observed many times before, when you bring gamma near to these deformed operators, what happens is because of this deformation, so I pointed out before that without the deformation, if x was equal to 0, these operators would have a 0 of order z of order w at the insertion point z prime. That was this property of this spectral flow ground state. But if you deform by x, then it is x plus this. And that should remind you, of course, of the property of the covering map gamma. And so with these operators now, the proposal is the following. So we now have an honest string background, C equal 26, even has a current algebra symmetry, but in particular, we are Zora symmetry. We have these vertex operators. These are physical states, and we can, according to the rules of good perturbative string theory, we can compute amplitudes in this theory. They will depend, of course, on the choice of momenta, J nu, along this phi direction, spectral flow numbers, choices of size, number of points, and so on and so forth, and on the genus of the calculation, and of course on the parameter that tunes the interaction, and that's the quantity. And our claim is that these quantities, by construction more or less, by construction means by construction of these interactions, these two interaction terms, they reproduce order by order in the coupling, and with lambda equal to 2 mu squared, order by order in the coupling, and order by order in 1 over n, the symmetric product orbifold correlation functions. And since I'm running out of time, or ran out of time, yeah, I ran out of time. So let me just say in 2 words, and then I can, of course, give more details later in discussion if it's desired. Remind you from the second part, we had this formula with insertions at the poles, insertions of spectrally flowed 2 operators at UA, and then the W spectrally flowed operators at Z nu. Now, these operators here at the poles, these are really physical states, and these are precisely the psi minuses that are inserted there. So these operators here are not physical states. They're not exactly the psi minus. So what happens is essentially that the psi minus, insertion of the psi minus, when you bring them down. So, okay, once more, okay, this is going maybe a tiny bit too fast, but I should say, emphasize here again. Here, this is now really a string amplitude, right? Different from previous thing. Now, everything here is integrated. They integrate over the insertion point of the fields. I integrate over moduli of the surface. More generally, if I'm homogeneous. So this is a real string amplitude. And the claim is that this string amplitude is related to the CFT correlation function that I had before. And of course, that uses heavily this insight that came from within this community over the last years, that somehow this field gamma that we have in this Katsuaki-Moto representation, in some sense, in this type of correlation functions, that one has to compute in the worldsheet theory of the string theory, localizes to the branching function. And so if you, with that insight, you can, that is very well established, you can now see what happens. So these psi minus basically just create, they create the poles that you can see from the OPE and gamma. And so these, I would say, are polar sheet creating insertions. So every time you bring down one of these interactions psi minus from your theory, you create sort of a pole that is kind of a sheet of your branch cover. And if you have a minimal number of sheets created, then eventually you can get a non-zero amplitude. The minimal number is given by this R0. And then the second term can't really contribute or gives trivial contribution to the psi plus term because of what I alluded to before, that it sort of corresponds to a cycle of length 1, which is trivial in the symmetric orbifold theory. So it won't really matter. But then you can actually start inserting more than the minimal number of these psi minuses. And now something interesting happens is that now you can actually get contribution from the psi plus, phi plus, but only sort of from the boundary of their integration domain. When two of these guys, pairs of these things start to collide, in that case, if you remember these phi plus, they had spectral flow number 1. But when you have an OPE of 2 of them, they can produce contributions to spectral flow 2, and these were the ones that appeared in this formula. And by this mechanism, by this kind of condensation of pairs of these phi plus in the presence of more than the minimal number of sheet creating operators interactions phi minus, you can actually order by order reproduce precisely the CFT formula we had before. Okay, so this, of course, was super fast and probably not entirely convincing, but let me just conclude here. So I hope I was still enough to convince you that we were, in fact, able now to rewrite with the caveats that we discussed initially when you asked this question, the perturbative expansion in the deformed symmetric orbifold theory. in terms of bosonic string theory. And I did this, so the bosonic string theory is this theory here with two interactions, the sheet creating interaction psi minus, which is fairly conventional, and then this branch cut creating screening charge, which corresponds to the deformation of the symmetric product orbifold. And I did this relation without computing a single correlation function. This is what I had stressed at the beginning. So that's, of course, what I was after, to be able to engineer the interaction of this kind of dual description without solving the CFT before. Okay. So the final formula is this formula that, yeah, I've almost derived for you, except of course for being very sketchy in the final part. And that says that this correlation function, symmetric product orbifold, deformed symmetric product orbifold, are really, honest to God, sort of string amplitudes in this theory with these interactions. Now, zooming out, maybe one final comment. Of course, I pointed out before, and we discussed it also before, that this lambda, of course, in this formula here on the Liouville side is not really a parameter. It's just, it's switched on. That means the theory is interacting. So similar here, of course, this mu is not really a real parameter. That's, of course, a little different from like real Yang-Mills or gauge theory, where lambda is really a coupling that you can tune. I think in that sense, maybe it would be interesting to extend already this kind of correspondence to the boundary case. I think that's also something that is in our minds. So if you have boundary Liouville theory, of course, you have an honest coupling of the boundary strength, and then I think you can actually produce really a family of such formulas. So that would be one obvious extension. There's certainly lots of other extensions, but I really don't have time to discuss. Maybe we can discuss that together after. So let me thank you for attention, and sorry for going over time a little bit. Okay, thank you. Good. So,
Yeah,